Hello, my name is Mary Roth, and I am a research scientist at the IBM Almaden Research Center. In this session, I will lay the groundwork for data integration research and technology by describing a little bit of the history that led to the need for data integration techniques. Efforts to standardize how data was accessed and stored began to take off in the 1950s and 60s, as both corporations and government organizations began to increasingly rely on computer processing. Two prevailing models began to emerge: the hierarchical data model and the network data model. The hierarchical data model was popularized by IBM through its IMS product in the mid-1960s. With the hierarchical data model, data is structured strictly as a tree of records, such that records are connected through links and have a record having only one parent but multiple children. In 1969, the Database Task Group published a specification for the network database model, also known as the codicil data model. Unlike the IMS data model, the codicil model allowed records to have multiple parents, leading to a general graph or network data model, allowing for more flexible ways to represent relationships between data items. For example, in the hierarchical model, a library might be organized as categories of books, and the categories are organized by country of origin, such that each data record had only one parent. In the codicil model, the books in the library have three parents: the library itself, the book's category, and its country of origin. These data models prevailed for much of the 1960s and 70s, and in fact, there are still important active IMS applications running today. However, both data models had a fundamental drawback, because the data was physically stored and organized on disk according to the data model itself. This meant that if the data model changed, the data had to be reorganized, and the applications that accessed the data also had to change. For example, suppose the library decided to split one of its existing categories into multiple categories. To make these changes to the data layout, it was often the case that the entire system had to be brought down, which introduced the need for scheduled outages and downtime. This was a major challenge for organizations to manage. In the early 1970s, Ted Codd introduced the relational database model, which enabled true data independence. Users specified only what data to store and what data to retrieve, but not how. The details of how it was stored and retrieved were handled internally by the database itself. This revolutionized the way we store and retrieve data. The relational data model provides a structured, organized, and application-independent way to store and retrieve data. Data is described declaratively by a schema. A schema can describe many different types of entities: books in a library, or books in a bookstore, or even groceries in a grocery store. Data records themselves no longer physically contain links to other related data records, but instead, data is related through the values of common fields, such as book titles or product names. This organizational model meant that the schema could be changed and the data could be restructured or reorganized without causing the applications that access the data to change. In addition, with the introduction of a powerful query language, such as SQL, data could be quickly and efficiently retrieved via arbitrarily complex queries specified in the language. The ability to isolate applications from how the data they accessed is stored and retrieved was a powerful feature. And by the 1980s, most commercial and government enterprises were adopting relational database technology to run all aspects of their business. Financial institutions and insurance companies were among the first to rely on relational database systems to keep track of bank accounts and insurance claims, mostly running on mainframe computers. By the 1980s and 1990s, the increase in computer sales and the introduction of the PC and workstations made relational database technology more accessible to other commercial enterprises as well, including retail chains, airlines, and even mom-and-pop shops keeping track of their inventory on a PC. The widespread adoption of relational databases led to multiple vendors, such as IBM, Oracle, InfoSphere, and Microsoft, providing the technology, and led to SQL as becoming the de facto standard query language. Eventually, the explosion in relational database use led to new desires, to easily and quickly combine data stored in different relational databases. For example, companies with locations in multiple different geographies, such as a bank with multiple branches, might want to ask queries that span those different databases, such as to compute the total number and value of accounts across all of its branches. As another example, corporate mergers and acquisitions became quite popular in the 1980s and 1990s, and often resulted in an enterprise having its crucial data spread across different databases, usually created by different vendors. Though relational databases provided data independence and isolated applications from the details of how data was stored and retrieved, they did not isolate applications from the details of integration. All logic to combine and connect data stored across relational databases had to be handled at the application level. Dealing with data integration at the application level can be both difficult and tedious. For example, suppose we had 3 locations that contained information about books: the UC Santa Barbara Library, the UCLA Library, and the UCLA Bookstore. The first challenge in data integration is physical. If the data is stored at different locations, what is the optimal way to combine it? By the 1990s, much thought had already gone into the most efficient way to store and retrieve data. Most relational databases had a fairly mature storage mechanism and sophisticated query optimization techniques. But they were all based on the assumption that the data was stored locally and the database itself had full control over the data. Thus, none of these techniques work to optimize retrieval across databases. What is the optimal way to combine data from the UC Santa Barbara Library Catalog and the UCLA Library Catalog? Should I move data from one site to another in order to answer the query? If so, which one? Should I filter the data before joining it? The second challenge in data integration is descriptive. How do I combine data that is described differently? In other words, how do I combine data that is similar in nature but is organized by slightly different schemas? In this example, the UC Santa Barbara Library Catalog stores the author's name as one field in the record, while the UCLA Library Catalog stores the author's first and last name in separate fields. Even though both catalogs describe books, I cannot write one query that combines data from both catalogs without some sort of transformation to reconcile the difference in how authors' names are represented. The third challenge in data integration has to do with how data is identified. In other words, how do I combine data that is represented differently in different sources? In this example, the library catalogs use a Dewey Decimal Number to uniquely identify a book, while the UCLA bookstore uses an ISBN number instead. Again, I cannot match data about the same book from 2 library catalogs with the bookstore without some mechanism to map Dewey Decimal IDs to the ISBN number. Beginning in the late 1980s and early 1990s, the research community took up these 3 challenges and formally established data integration as an active area of research. Let's look at the approaches taken to address each of these challenges in a little bit more detail. Let's start with challenge 1. How do I query and combine data that is physically stored in different places? It really comes down to who is going to move, the query or the data. There are 2 basic approaches. The first approach is data federation. And in data federation, a global schema describes the integrated data, and the query over the global schema is decomposed into partial queries, which are then sent to each of the sources to execute, and the answer to the integrated query is assembled from the partial results. For example, to retrieve all of the books of fiction in the 2 libraries, a query would be sent to the UCLA Library Catalog, and the UC Santa Barbara library catalog to retrieve the titles at each library, and then the final list would be composed as a union of the two partial lists. The second approach is data warehousing. Data warehousing creates a relational database from the data to be integrated by moving the data from all sources to a central place where it is described by an aggregated target warehouse schema and can be queried with the full power of the relational database. In this example, you can see that the new schema removes duplicate titles and introduces a new table to record how many of each title are available at each library. Let's take a closer look at federation. How does it work? Federation works by taking a traditional relational database architecture and removing the assumptions that the data is stored and controlled by the database engine itself. Instead, the database engine becomes the federation engine or mediator. The federation engine maintains a global target schema to provide a virtual view of the integrated data, and federation metadata keeps track of which sources provide which sets of data. The query optimizer uses this federation metadata to decompose a query over the global schema into partial queries that can be executed by each of the sources. The federated query optimizer interacts with wrappers for each of the sources to map the global schema to the schema of the original source and to negotiate how much of a partial query the source can do and at what cost. When the query is executed, the federated query engine interacts with the wrappers to retrieve the partial results from each of the sources. The wrapper translates the query into the native language of the sources and returns the results back to the federated query engine. In this case, we have two types of wrappers, one that understands SQL for the two relational sources, and one source that understands REST APIs. The federated query engine post-processes the partial results to assemble the final result of the query. What kind of post-processing is involved? Well, it may be that the original source is a relational database, such as the UCLA and UC Santa Barbara library catalog databases. In this case, it often makes sense to push as much of the processing to the original source as possible to minimize the amount of data to be returned to the federation engine. On the other hand, it may be, for example, that a source has limited query capabilities, such as the REST API wrapper, which can only retrieve data by title. Thus, if the query to the federated database is to return all titles of fiction, the request to the REST wrapper would be to retrieve all books, and the final filter on category must be applied by the federated query engine. An alternative to data federation is data warehousing. Data warehousing goes hand in hand with a process called ETL, for extract, transform, and load. With a data warehouse, a new schema is created to provide a materialized view of the data sources at the warehouse itself. This warehouse schema might add and aggregate additional metadata to the data from the original sources. In this example, the warehouse schema shows one table to describe all books and adds a second table to record how many of each title are available at each location. ETL processes regularly extract data from the original sources and perform steps to transform the data so that it can be loaded into the warehouse according to the warehouse schema. The ETL process is run by an ETL engine that can perform fairly arbitrarily complex transformation steps, often in parallel, including removing duplicates, performing joins, and other sophisticated operations. The populated warehouse is a fully functional relational database, and full SQL queries can be directly executed over the warehouse data. Now let's turn to challenge 2. Data federation and data warehousing provide powerful capabilities to physically integrate data from different sources. The next problem is that the data was likely modeled independently, which is the most common case in data integration scenarios. It is therefore likely described by different schemas and requires that the schemas be mapped to a common schema. The common schema is a virtual schema in the case of federation and a materialized schema in the case of data warehousing. Schema mapping is a declarative technique in which each source schema is mapped field by field to the target schema. For example, we can map the UCLA library schema and the UCLA bookstore schema to a target schema that unifies the data across both sources. The target schema includes data that is common to both sources, such as book title, as well as data that may only exist in one source, such as the book price. There may be a one-to-one correspondence between the fields in the source and target schema. In this example, that is the case for the UCLA bookstore data source. Each field of the source data record can be directly mapped to a corresponding field in the target data record. More commonly, there is not a one-to-one correspondence between the source and the target, as is the case with the UCLA library source schema. The UCLI source models the author's first and last names as individual fields, whereas the target schema models the author's name as a single field. The first and last name of a UCLA library book author can be mapped by way of a transformation function, such as concat, to indicate that the two source fields need to be concatenated to form the author's name on the target schema. Likewise, the target schema identifies the books by ISBN number, and so the source field that stores the Dewey Decimal Code for the book at the UCLA library must be mapped to the target ISBN field by means of another transformation function, such as Dewey to ISBN, to convert the Dewey Decimal Code to the ISBN number. Finally, since there is no price associated with books at the UCLA library, the constant value of 0 is mapped to the price field on the target schema. Schema mappings are development time activity, often specified through a user interface that allows a user to visually map from the source to the target schema. This activity creates a mapping specification, which is a declarative description of the transformations that must occur at runtime to convert the source data records into a form that matches the target schema. Once the mapping exercise is complete, this mapping specification can be interpreted to generate runtime conversion code into a format that is understood by the originating data source in the case of federation, or by the ETL process in the case of a warehousing tool. While the mapping specification is created once, the runtime code that is generated can be repeatedly executed to transform the data. Here, this example assumes that the data sources are integrated by federation. Since the UCLA library is a relational database, the runtime code that is generated to perform the conversion is an SQL query. Notice that the select clause for the query includes the transformation function specified in the schema mapping and includes the addition of a constant to map to the target price field. Data from the UCLA bookstore can be extracted via a REST API, and since the schema mapping was a straightforward one-to-one correspondence, the runtime code that is generated is a GET request to retrieve the fields of the data records. The conversion of the Dewey Decimal Code on the previous slide is instructive of the third challenge in data integration. Data that represents the same entity can be represented differently across different data sources for a variety of reasons. Often, data is dirty and contains inconsistencies and errors. Names and addresses, for example, often have multiple spellings, abbreviations, and misspellings, making it difficult to resolve that they refer to the same entity. For example, the UCLA library can be referred to by multiple variations on the name, and there may be different spellings, abbreviations, typos, or empty fields in its address information. Data cleansing is the exercise of cleaning dirty data to remove inconsistencies and errors. Data cleansing techniques are often rule-based, allowing a user to define rules to standardize how data is formatted. For example, to consistently use the two-letter state code for the US, and matching rules to identify data records that refer to the same entity. Furthermore, as we saw with the ISBN number and the Dewey Decimal Code, dirty data is not the only challenge. While the data may be of high quality and formatted consistently, the entities themselves may be identified by different information. In this case, entity resolution is required to link information that refers to the same entity. We will talk more about this in the next session. What I have just described are the three major areas of research focus in the early days of data integration. The introduction of the World Wide Web heralded a new generation of integration challenges. First, valuable data is being generated at an accelerated rate, and it is no longer under the tight control of DBAs and governed applications. This further complicates issues of data cleansing, deduplication, and entity resolution. Secondly, data is much more heterogeneous today. Data easily available via the internet is no longer as rigidly structured as it was with the relational data model. Documents, videos, audio, and scientific data come in a variety of formats, sometimes semi-structured and sometimes with no structure at all. Finally, the proliferation of data due to social media, the Internet of Things, and scientific data requires very careful attention to the efficiency of the techniques used to combine, search, and query data. In the next session, we will continue to explore these challenges in more detail. But before we leave this session, I will include a list of relevant publications. Thank you all for your attention.